Welcome everybody to the Quantep seminar. We have 225 people watching. That's great, from many places around the world. So welcome everybody. So I would like to start by introducing my co-organizers in this seminar. Andris Ambainis from Riga, Latvia, Simone Montangero from Padova, Italy, and also João Seixas, a colleague here from Lisbon, where I'm based, who is just arriving. Of course, I also want to welcome and thank our speaker, John Preskill, whom I introduce in a minute. Before that, I also want to thank the local team here in Lisbon, Sagar Pratapsi, Duarte Magano, and Diogo Cruz, who set up all the electronic logistics to make this seminar happen. So the idea of the Quantep seminar, Quantum Computation and High Energy Physics seminar, is to share and discuss ideas at the frontier of quantum computation and high energy physics. And the vision for the future is, in fact, to go beyond quantum computation one day and consider other quantum technologies, but that's a vision for the future. The focus now is quantum computation and quantum simulation, and how these can potentially help tackle challenges in different aspects of high energy physics, but also in turn to see how high energy physics can give us insight into quantum information and how to explore that frontier. So we already have three seminars scheduled for 2020. We start today with John Preskill, and then in November, in the first Wednesday of November, we have Saul Wan, and then in the first Wednesday of December, we have Ignacio Sirac, who will be discussing different aspects of this rather recent frontier. And we already have speakers in line for 2021, which we will announce timely. So thank you very much. Thank you very much to the now 310 people watching this seminar. We hope this becomes a venue to develop a fruitful dialogue between these two communities, the quantum computation community, the high energy physics community, and explore novel or even old ideas at the frontier of these two fields. So I would like to thank once again John Preskill. We are very honored to have you here as the inaugural speaker for our quantum computation and high energy seminar. John Preskill is the Richard Feynman Professor of Physics at Caltech. He's live from California, quite early morning there. So we try to optimize the schedule to cover as much as possible of the globe. We go from late afternoon and evening in Eastern Europe to very early in the morning in California. And through YouTube, people will be able to catch this talk later, including in other parts of the world. So John has been a pioneer of quantum information. I think many of us, starting by myself, we learned quantum information from the famous lecture notes, extremely pedagogic and high quality, that John published in his site already in the 90s. He's been one of the pioneers of quantum information, and given his background and taste in high energy physics, cosmology, field theory, topological problems, so he's just a theoretical physicist, and exploring these connections to quantum information, he very early on set a vision and to some extent even an agenda, and made very important contributions. And for example, a famous one for error correction amongst many others, also contributing even in terms of the terminology we used, and amongst many other achievements he created, I think 20 years ago, the Institute for Quantum Information at Caltech. So one of the first institutes devoted to what at the time was a novel and nascent field of quantum information, quantum computation. So John, it's a great pleasure and honor to have you here. You've also been one of the people who quite early on has been pointing out the connection between quantum information, quantum computation, and high energy physics, and how they can dialogue and progress from this dialogue, including concrete scientific results and again, a vision. So it's a great honor and privilege to have you here inaugurating our quantum computation and high energy physics seminar. Thank you very much. And we'll take questions in the end.
Well, thank you very much for the generous introduction and for the opportunity to speak here. I want to talk about three things. I want to say something about the current status and the prospects in the near term for quantum computing. Then some of the opportunities afforded by quantum simulation and quantum field theory. And then some of the work in progress I'm doing with collaborators listed at the bottom of the slide on simulating quantum field theory with both classical and quantum algorithms. And a summary of the message is that we've learned a lot about quantum field theory using classical computers, and with exascale computers, we will continue to advance our knowledge of quantum chromodynamics in particular, but there will be some challenges that will remain, particularly concerning the real-time evolution, like scattering processes and the properties of nuclear matter and the quark-gluon plasma as a function of temperature and chemical potential. We don't expect that classical computers will ever be able to address these problems efficiently and accurately. With quantum computers, it will be possible in principle, though we're not sure at this stage exactly when that's going to happen. The big physics payoff may still be a ways off, but the research we do now can bring us closer to an era in which quantum simulation fuels progress in fundamental physics. And even in the near term, studies of dynamics in strongly coupled many particle systems can provide insights that are useful to high energy physicists. As a physicist, the way I like to look at the field of quantum information science is that we are still in the early stages of the exploration of a new frontier of the physical sciences, what we could call the complexity frontier or entanglement frontier. We are just now developing and perfecting the tools to create and precisely control very complex states of many particles, highly entangled states that are so complex that we can't simulate them accurately with our most powerful classical supercomputers or understand their behavior very well with existing theoretical tools. And that opens opportunities for physics discovery. Our conviction that this frontier will be fruitful to explore rests on two central ideas: quantum complexity, our basis for thinking that quantum computing will be powerful, and quantum error correction, our basis for believing that we can scale up quantum computers to large systems that can solve hard problems. And both of those ideas rest on the underlying concept of quantum entanglement. The word we use for the characteristic correlations among parts of a quantum system, which are different from the correlations we normally encounter. We can envision it this way. You can imagine a book which is 100 pages long, and if it's an ordinary classical book written in bits, every time you read another page, you learn another 1% of the content of the book. And after you've read all of the pages, one at a time, you know all the information that's in the book. But suppose instead it's a quantum book written in qubits where the pages are highly entangled with one another. And then when you look at an individual page, you see only random gibberish, which reveals almost no information that distinguishes one highly entangled book from another. The reason is that in the quantum book, the information isn't encoded in the individual pages. It's stored almost entirely in the correlations among the pages. And if you want to read the book, you have to make a collective observation on many pages at once. That's quantum entanglement. It's very different from any notion of correlation that applies in everyday life. And what's quite interesting about the entanglement among qubits is that it's very complex to describe using ordinary classical information. So for a typical highly entangled state of just a few hundred qubits, if I wanted to write down a complete description of all the correlations among those qubits, I'd have to write down more bits than the number of atoms in the visible universe, which is never going to be possible. Now, that in itself doesn't mean that quantum computers can do things that we care about, but we do have some reasons for thinking that quantum computing will be powerful. First of all, we know of examples of problems that are believed to be hard classically, which in principle quantum computers can solve efficiently. Finding the prime factors of large composite integers is the best known example. And we think factoring is hard because really smart people have tried for decades to find better factoring algorithms, but still the best algorithms that we have a runtime which is super polynomial in the number of digits in the number to be factored. The computer scientists have provided complexity theory arguments based on reasonable assumptions, indicating that we can do a modest sized quantum computation and measure all the qubits, and that by doing so, we are sampling from a probability distribution that we can't sample from efficiently by any classical means. But perhaps most tellingly, we don't know how to simulate, in general, a quantum computer using an ordinary classical computer. That's not for lack of trying. Physicists and chemists have been trying for decades to come up with better algorithms for simulating highly entangled matter, but still the best algorithms that we have in hard instances have a runtime that scales exponentially with the system size, with the number of qubits. That's not to say that the power of quantum computing is unlimited, and we don't expect, for example, that quantum computers would be able to find efficiently exact solutions to hard instances of optimization problems. But it's a remarkable thing about nature that there are problems which we think are too hard to solve classically, but which we can solve quantumly in an efficient manner. And it's a compelling question. What are these problems which are classically hard and quantumly easy? And we've learned a lot of things about that in the last 25 years or so, but I think we have a great deal more to learn. But if you're a physicist or a chemist, there's a natural place to look for such problems. We expect that a quantum computer would be able to efficiently simulate any process that occurs in nature. We don't think that's true for ordinary classical digital computers, which can't efficiently simulate highly entangled matter. So with a quantum computer, we'd be able to go further, probe more deeply into the properties of complex molecules and novel materials, and also investigate fundamental physics in new ways, for example, by simulating high energy collisions of fundamental particles, or simulating the quantum behavior of a black hole, or the conditions in the universe right after the Big Bang. Now, it's not a new idea to use quantum computers to simulate nature in this manner, to simulate quantum phenomena. Feynman proposed it almost 40 years ago. And after 40 years, we're just now getting to the stage where quantum computing is capable of doing interesting things. So evidently, making a quantum computer is hard. What makes it hard is that in a quantum computer, we want to simultaneously satisfy a set of criteria that are nearly incompatible with one another. We want qubits to interact strongly with one another so we can efficiently process the information they encode. We don't want the qubits to interact with the outside world, which would lead to decoherence and cause a computation to fail. But we do want to control the qubits from outside to execute an algorithm and eventually to read out the qubits to find the result of a computation. It's very hard to build a platform that realizes all of these desiderata. So it's only after decades of progress in materials and qubit design, in control protocols and so on, that we've gotten as far as we have. It's quite important to isolate our quantum computer from the environment during a computation because the enemy of the quantum computer is decoherence, which can cause errors in quantum data. So we can't expect to operate a large-scale quantum computer unless we have a way of protecting it from such sources of error. And the essential difficulty is a fundamental difference between quantum information and classical information, namely that whenever we observe a quantum system, we disturb it in some uncontrollable way. So to do a quantum computation accurately, we have to, in effect, keep the quantum data nearly perfectly isolated from the outside world during the computation. Well, that sounds very difficult because our hardware is certainly not going to be perfect, but we've understood in principle how to do it using the idea of quantum error correction. The essential idea is that if we want to protect quantum information from damage due to decoherence and other sources of noise, then we should encode it in a highly entangled state with many parts. The environment will interact with those parts locally, one at a time, but looking at just one of the parts reveals none of the encoded information, just like for that 100-page book I described earlier. So the information is well concealed. And furthermore, we've learned how to efficiently process quantum information that's encoded in this highly entangled form, which is well protected from error. Any qubit has to be realized physically in some way. We like to think of qubits abstractly, but there are many different ways of physically realizing a qubit. For example, in a fundamental individual quantum system, like a single photon or electron or an atom, those are quite remarkable encodings because they're such simple systems, microscopic systems, but we've learned how to control them very accurately in the lab. Or it could be encoded in a more complex way, for example, in an electrical circuit at very low temperature. And that's also a remarkable encoding since it involves the collective motion of billions of electrons, and yet we're able to control it as though it were a single atom. And it's important that all of these different hardware approaches continue to advance in parallel, and others as well, because we don't really know at this stage which hardware approach has the best prospects for scaling up to large devices that can solve very hard problems. So where is the field today? Arguably, we have reached a milestone that has been called quantum computational supremacy that was announced with some fanfare last year by the Google group. The Google group constructed a device which they call Sycamore. And the motivation for their experiment was that one of the most remarkable things we know about the difference between classical and quantum systems is we think classical systems cannot simulate quantum systems efficiently in general. And that's a fact about nature for which we have a very strong incentive to the extent that we can, try to validate it in the lab. Sycamore is a device with 53 working qubits laid out in a two-dimensional array where entangling two qubit gates can be performed between neighboring qubits in the array. And what they did is they executed quantum circuits with up to 20 layers of these two qubit gates. The gates are noisy, so the final result of the computation when all the qubits are measured is quite noisy, with a success rate of about 1 in 500. So if you run the computation 500 times, you get random junk about 499 times and something of value just once. But they can execute the computation millions of times in just a few minutes in order to extract statistically useful results. If a classical supercomputer were to attempt to simulate what this quantum circuit does, it's hard to do. It would take, it's estimated, at least days and possibly much longer to do that classical simulation. And furthermore, the cost of doing the classical simulation grows exponentially with the number of qubits. So as the system grows from 53 to 60 to 70 qubits and beyond, the simulation quickly becomes far out of reach. So we can conclude that hardware is working well enough now to produce meaningful results in a regime where classical simulation is difficult. So that's an impressive achievement for the experimental physicists. It's a testament to the progress that's being made in building quantum computing hardware. Arguably, we've now entered the regime where the extravagant exponential resources of the quantum world can be validated. That's not really a surprise, but it's a milestone to be acknowledged for technology on our planet. Building a quantum computer is very hard. Scaling it up is hard, but not so ridiculously hard that we can't continue to make progress. And we can begin to think about serious, useful applications. But the particular task performed by Sycamore was not of any intrinsic practical interest other than for the purpose of demonstrating quantum supremacy. It's useful to have a word for the era in quantum information processing that's now dawning. So I made up a word, NISQ, noisy intermediate scale quantum. Intermediate scale to emphasize that these are devices of sufficient scale that it's difficult by brute force to simulate what the quantum device does with a classical supercomputer, but noisy to emphasize that these devices are not error corrected and the noise limits their computational power. It limits the depth of a quantum circuit that we can execute with useful signal to noise. Now for physicists, NISQ is exciting. It means we have an opportunity to explore in the lab the properties of many strongly interacting particles in a regime which hasn't been experimentally accessible before. And it may have useful near-term applications, but we're not really sure about that yet. We shouldn't think that NISQ is going to change the world by itself right away. It should be regarded as a step towards more powerful quantum technologies we expect to develop in the future. I am confident that quantum computing will have a transformative impact on human society eventually, but we're not sure how long that's going to take. There are several emerging paradigms for how near-term quantum devices might be used to solve problems. For example, hybrid quantum classical schemes, it makes sense to get as much power as we can out of our classical computers and then to boost that power with a kind of quantum coprocessor. It might work like this. We can execute a quantum computation of modest size and measure all the qubits, feed those measurement outcomes to a classical computer, which returns instructions to slightly modify the quantum computation. And that cycle is iterated until convergence, with the goal being to minimize a cost function for the purpose of finding an approximate solution to some optimization problem. As I've already said, we don't expect a quantum computer to efficiently solve exactly the hard instances of NP-hard problems, but it might be able to find better approximate solutions or to find approximate solutions faster. So should we expect that these NISQ optimizers will be able to solve problems of interest with a speed up compared to the best classical computers running the best algorithms for solving the same problems? Well, we don't really know. We'll have to try it and see how well it works. But it's really a lot to ask because the classical algorithms have been well honed over decades of development, and these NISQ processors are just becoming available for the first time now. Now, we don't necessarily have to be discouraged that theorists are unable to give us a convincing argument that NISQ processors will be powerful. We do know lots of examples in classical computing of algorithms which turned out to be powerful and useful, even though theorists were not able to validate that power in advance. People had to experiment with the algorithms to find out what they could do. A good example is deep learning, which is having a big impact on the world, even though we still have a very limited theoretical understanding of why, for many cases of interest, deep learning networks can be efficiently trained. And quantum computing may be like that for a while. We will try various heuristic algorithms without any guarantee of successfully finding speedups. And there are various ideas for approximate optimization and other applications that we'll try, and we'll experiment with them, and we'll improve those algorithms as we learn more. But in the near term, it's going to be challenging to find impactful applications if we're limited to of order 100 qubits and circuit depths less than 100. It will require a vibrant dialogue between the application users and the quantum computationalists to find interesting applications. We might have to get lucky. Now, as I've emphasized, these NISQ devices are not protected by quantum error correction. We think the long-term solution to the noise in quantum hardware will be quantum error correction. But quantum error correction has a very high overhead cost in the number of qubits we need and the number of gates. Now, how high that cost is depends on the quality of our hardware and the complexity of the algorithm we want to run. But as an example, a recent estimate is that if I wanted to use a quantum computer to break widely used public key crypto systems, and I had a gate error rate, an error rate per gate for entangling 2-qubit gates of 1 in 1,000, which is somewhat better than has been demonstrated in the Google experiment, I could execute the algorithm in less than a day using superconducting quantum technology, but I'd need about 20 million physical qubits to have sufficient redundancy for the error protection to work successfully. So we have a long ways to go from where we're likely to be in the next few years with hundreds of physical qubits to devices with millions of physical qubits, and that's probably going to take a while. But in the meantime, it's important to continue to advance the fidelity of quantum gates, the systems engineering, the design of algorithms, the error correction protocols, and so on, to bring us closer to the arrival of a really scalable, fully fault-tolerant quantum computer. Now, an area in which we expect quantum computers to have a significant impact of special interest to physicists in particular is quantum simulation, in particular the simulation of dynamics. Classical computers are especially bad at simulating the dynamics of highly entangled quantum systems. So quantum computers are expected to have a big advantage in that arena. And we might learn interesting things about dynamics already with devices in the NISQ era. One could argue that that's happening already. A useful analogy may be that we learned a lot about chaos, about sensitivity to initial conditions in classical nonlinear systems in the 60s and 70s when people started doing large-scale simulations on digital computers of those nonlinear systems. At this point, we understand comparatively little about chaotic dynamics in quantum systems because we can't simulate that. And simulations of modest scale may already lead to revealing insights. In the near term, our quantum simulators can be either digital or analog. By digital, I mean a universal quantum computer, gate-based, which in principle can simulate any local Hamiltonian of interest when suitably programmed. And by analog, I mean a highly tunable quantum system with some native Hamiltonian, which resembles that of a model system that we want to study. It's important to pursue both of these avenues. The analog simulators are more advanced at this stage. Analog quantum simulation has been an active research area for 20 years, and digital quantum simulation is really just starting now. In principle, digital simulators have greater flexibility in the Hamiltonians that we can simulate in the initial states we can prepare, and we can also use hybrid quantum classical methods, offloading some of the computational tasks to a classical computer in that case. But gate-based simulations of time evolution are quite expensive. So most likely our experience with near-term digital simulations of quantum evolution in the near term will be aimed at laying the foundations for the fault-tolerant simulations that we expect to be able to do in the future. And that remark really applies more generally to NISQ devices. So what kinds of things do we anticipate eventually being able to do in simulations of quantum field theory, which go beyond what we can learn from the Euclidean Monte Carlo simulations running on classical computers? Well, we should be able to simulate from first principles ab initio with no phenomenological assumptions the collision of hadrons in a high energy experiment in QCD, something of interest for understanding backgrounds at the LHC. We should be able to accurately characterize properties of nuclear matter and the quark-gluon plasma of interest in early universe cosmology and the astrophysics of neutron stars, to simulate the electroweak response of a hadronic matter, which is important for experiments at the intensity frontier, to simulate nuclear reactions in QCD of interest, say, for astrophysical modeling, and also to explore properties of other strongly coupled quantum field theories beyond the standard model for investigating possible models of new physics. And simulation of quantum field theory can be a stepping stone towards a deeper understanding of quantum gravity, especially because, at least in the case of quantum gravity in anti-de Sitter space, it's related to a quantum field theory through holographic duality. And we can expect that just thinking about how to simulate quantum field theory on a quantum computer will lead to new insights. That's certainly been the case for the Euclidean Monte Carlo simulations. Generally speaking, what a quantum simulator can do, which is hard to do in a classical computer simulation, is sample accurately from the outgoing states in the simulation of some process like a scattering event to compute real-time correlation functions, including at non-zero temperature and chemical potential, and to study transport properties and phenomena far from thermal equilibrium in strongly coupled theories. A typical quantum simulation task has 3 steps. The first is the preparation in the quantum computer of some initial state. For example, incoming scattering state, if I want to simulate a scattering experiment. The second stage is time evolution governed by a Hamiltonian. We use the Hamiltonian formulation of quantum field theory in simulations on a quantum computer, simulating the evolution by some sequence of discrete steps with a controllable error. And at the end, we measure an observable, for example, an observable that might be measured by some detector after a scattering experiment occurs. And the goal of such an algorithm is to sample accurately from the probability of distribution of outcomes in the ideal process. And as theorists, we can investigate how the computational resources that we need to do such a simulation scale with the error we're willing to tolerate, the size of the system, the total number of particles, the total energy, the energy gap of the system, and so on. Where the typical resources that we usually care about are the total number of qubits needed and the number of gates in an ideal computation. And what we've been able to show in some of our work on simulations of scalar and fermionic field theories is that algorithms exist for which the resources needed do scale polynomially with all of these input parameters. And we don't think that's possible in a classical simulation. It's important to be able to efficiently prepare the initial state of interest, but the processes that we care about in physics that actually occur in nature involve states that are easily prepared, or at least so we believe. A quantum field theory ideally has a number of degrees of freedom per unit volume, which is infinite, so it needs to be regulated to put it on a computer, whether it's a classical or quantum computer. Typically, we consider the fields living on a lattice in space with a bounded number of qubits describing the field at each one of the lattice sites. And that lattice spacing and the truncation of the field are additional sources of error that we have to investigate carefully. So what are the kinds of things that we should simulate? Well, let's ask, what is the best hope for doing a simulation of quantum field theory in the relatively near term that would teach us something new? And there are a lot of possible answers to that question. But to make life easy, I'm going to suppose that we're talking about simulating a process in one spatial dimension, since that's easier than simulating higher dimensional physics. Now, in one spatial dimension, we have pretty good classical methods for simulating dynamics. So we should ask, where do those classical methods fail, where a quantum simulation might still succeed? And the general answer to that question is the classical methods become too inefficient when states become very highly entangled. So we might imagine a scattering process, for example, just in one spatial dimension, where 2 particles collide at very high energy, producing many outgoing particles. We can envision the process as one in which the 2 colliding particles produce a kind of fireball, which then boils off particles with some characteristic temperature. And for the purpose of getting a crude estimate, let's suppose that temperature is independent of the total energy of the process. So the number of particles produced would scale linearly with the energy, and the entropy, the thermodynamic entropy of the particles that leave the collision region traveling to the left or to the right would also scale with the number of particles. But if the incoming state and outgoing state are both pure states, that thermodynamic entropy is really entanglement entropy. It arises because of entanglement between the particles moving to the left and moving to the right. And the cost of simulating that entanglement is actually exponential in the entropy if we simulate it on a classical computer. So in a process in which we produce, say, 20 particles or so, it's likely that classical methods will break down and it'll be prohibitively difficult to do a classical simulation. Well, in our work, we thought it would be particularly interesting to consider simulating in one dimension a scalar field theory in a broken symmetry phase. So we'll consider just a single real scalar field with the Hamiltonian shown, where the potential for the field has two degenerate minima at the field phi equals v and phi equals minus v. So that Z2 symmetry, under which phi goes to minus phi, is spontaneously broken. There are two vacua, one in which phi is equal to plus v, one in which phi is equal to minus v, at least classically. And we can consider a configuration in which we have the plus vacuum on one side and the minus vacuum on the other side. And so interpolating between those two vacuum states, there will be a domain wall, I'll call it a kink, which in one spatial dimension behaves like a particle. And as we go to the classical limit, that kink becomes very heavy. It has a size which is determined by the Compton wavelength of the lightest particle in the theory, or the lightest meson, but it has a mass which grows as the theory becomes more and more weakly coupled. So as we approach the classical limit, I can imagine colliding a kink and an anti-kink, and in that collision, many light particles will be produced. And that's a process that I can study using classical field theory fairly accurately. But if I consider the collision between the kink and the anti-kink when the theory is strongly coupled, it's not obvious exactly what's going to happen. So that's the type of process that we're interested in simulating. And what's interesting about that is that in principle, it generates lots of entropy if we have enough energy to make lots of particles. And if that entropy is interpreted as entanglement entropy, we expect that to be hard to simulate classically. Another thing that's interesting about this broken symmetry theory is that the preparation of the initial state is kind of tricky. The standard method for doing initial state preparation in quantum simulation algorithms is the adiabatic method. That is, we start out with some theory for which it's easy to construct the state of interest, like two wave packets that are going to collide. That's actually easy to do in the free non-interacting theory. And then as the system evolves in time, we imagine slowly turning on the coupling, which dresses the wave packets. They become the wave packets of the interacting theory, which can then collide. But we can't do that preparation by that adiabatic method in the broken symmetry phase, because we would have to cross a phase boundary to get from the free theory to the broken symmetry theory. The kinks don't exist in the free theory. So that's somewhat analogous to the problem we'll have to prepare an initial state for scattering in QCD. If I'd like to consider two protons colliding with one another, preparing those initial states in a quantum computer is not something we can sensibly do starting with the free theory, a theory of non-interacting gluons and quarks. And in fact, the analogy goes further than that. In QCD with many colors and large N QCD, the proton has a fixed size and becomes heavier and heavier as we go to larger and larger N, the number of colors. And in our broken symmetry scalar theory, the kink has a fixed size and its mass grows larger and larger as we go to weaker and weaker coupling. So this is sort of a stand-in for the more difficult state preparation problem that we'll eventually have to face in QCD. And there are two types of simulating this process that we've investigated, two different methods. One is kind of a brute force simulation of the field theory, which is similar to the method that we've used in our earlier work to study the scaling of quantum resources with input parameters. And the nice thing about that is that we can do error estimates and we can make statements about the performance guarantee in the algorithm, what resources we'll need to attain a certain error. But there's another method which will be much easier to do in the lab, and that is to just study a spin system, in this case, a spin chain with just a single qubit per site is enough. And if it goes close to a critical point, that system will be described by an emergent field theory that we can study, and we can investigate what happens when particles collide in that emergent theory. Now, that's a more heuristic method where we don't have a rigorous way of estimating errors, but it's of interest because it's something that we're likely to be able to do sooner with quantum platforms. It's also interesting in its own right, just from the spin dynamics point of view. So the nice thing about one-dimensional physics, and which makes it possible to do a lot of accurate and interesting simulations with classical computers, is that in systems that have a mass gap, where there are no massless particles, the low energy states are only slightly entangled. And that means they can be well approximated in a classical description, a succinct classical description, as matrix product states. I can think of that as essentially a product of matrices, where each one of the matrices carries an index, a physical index, which in our case corresponds to the field variables at a lattice site. And we do a tensor contraction summing over an internal bond index, and we can capture the entanglement well with a relatively low dimension bond index when the states are only slightly entangled, which is typically true of the vacuum and low-lying energy states. And so our idea here is just to, with a classical computer, find a good description using tensor network methods of the initial state. And then once that's been found on the classical computer, to compile the tensor network as a quantum circuit, which we can load into a quantum computer, which we can execute to load that initial state into our quantum computer so that the evolution can subsequently be studied. So in order to do that, we have to find the tensors that correspond to the plus vacuum in our spontaneously broken symmetry phase and the minus vacuum, and those are related to one another by the Z2 symmetry of the theory. But we also need to construct kinks where we would have minus tensors on one side of the kink and plus tensors on the other, and then some interpolating tensor in between, which we would optimize by a classical algorithm to get a good description of the kink. And the type of initial state that we're really interested in is a wave packet of a kink and an anti-kink. So that would be a configuration where we have minus tensors on the left and on the right, say, and plus tensors in the middle, with two of these interpolating tensors, and with weight functions which determine how those wave packets are distributed in space, and the weight functions have phases which tell us how they're distributed in momentum. Let's see, I think no, that's okay, I'll get to that later. Now, we'd like to see how hard it is on the classical computer to find this description of our initial state, a kink and anti-kink wave packet, which we can then load into the quantum computer. It helps that we're in one spatial dimension. That means that the field fluctuations at a site are not as robust as they are in higher dimensional theories. It also helps that this theory is what we call super renormalizable, and that means that the structure of the entanglement at short distances is similar to a free theory, so we can characterize it well for the purpose of estimating the errors in our algorithm. Now, the methods that are normally used by the computational physicists to find a MPS approximation to a slightly entangled state, the density matrix renormalization group method, is a heuristic method without any guarantee of convergence or any rigorous bound on the error. But fortunately, the computer scientists have developed a rigorous version of finding an MPS, the algorithm for finding an MPS, that we can make use of for the purpose of analyzing the complexity of constructing the vacuum state of our theory. But that's not quite enough for us because we want to construct this kink anti-kink state. And once we're in the kink sector, there's no longer an energy gap. And that energy gap was important in showing that it was efficient to find the MPS approximation in that earlier work. There's not an energy gap because once we have a kink, it can have any value of the momentum, which can be arbitrarily small. And so there's really a continuum of kink states. So we need an algorithm which will allow us to construct MPS approximations also to states in a sector where there is no gap. But fortunately, that problem has already been solved by means of what's been called the rigorous renormalization group. So we can make use of that earlier work as well. And essentially what we do is we find a kind of crude approximation to the kink anti-kink initial state of the matrix product state form. And then we apply a filter to it to get rid of unwanted excitation so we can get a good approximation. And applying that filter increases the bond dimension, but by some manageable amount. And so we can wind up showing that the initial state preparation on a classical computer scales almost polynomially. And of course, that's a worst case estimate. It's quasi-polynomial time. That doesn't mean that it's really going to be practical necessarily, but we wanted to address the question of principle of, is this a problem of manageable complexity? And what we found is that it can be done in quasi-polynomial time on a classical computer. And then once we have the MPS approximation, remember the idea is to load it into a quantum computer and to study the dynamics. But there's another approach which is much more feasible in the near term on quantum platforms that we should compare with. And that's the approach of just investigating the dynamics of a spin chain, where we have just a single qubit on each site on a lattice in one dimension. And what we studied is a Ising-like spin chain, a ferromagnetic spin chain with the Hamiltonian shown here. Here Z and X mean the Pauli operators, sigma Z and sigma X. So the Z term is a ferromagnetic term favoring that neighboring spins on the lattice align with one another. There's also an magnetic field pointing in the transverse direction, the X direction, which turns us into a quantum problem, so the states are entangled. And we also introduce some explicit symmetry breaking, a small component of the field in the Z direction, breaking that Z2 symmetry. And that's interesting to do for a couple of reasons. It means, in particular, that now there will be a true and a false vacuum of those two degenerate vacua when we turn on that Z component of the field. One will have the spins aligned with the field, the other anti-aligned, and that introduces a small separation in energy density per site between the two states. One is the true vacuum of the theory, the other is a false vacuum, which is locally stable, metastable, but can decay by quantum tunneling to the true vacuum, which itself is a process that's of interest in early universe cosmology. But what it also means is that if we have a kink and an anti-kink with true vacuum far to the left and true vacuum far to the right, there is false vacuum in between. And that provides a kind of confining interaction between the kink and the anti-kink. There's a string connecting them, and that pulls them together. It accelerates them toward one another, producing eventually a collision at high energy that might produce a lot of outgoing particles. So what we want to do is to tune this spin system close to a critical point where the correlation length is long. And then at long distances, it's described by an emergent field theory, which we want to be Lorentz invariant. We want it to have this spontaneously broken discrete symmetry. So we'll have kink states whose dynamics we can study, but we don't want it to be too close to integrable. If the theory is integrable, that means there won't be particle production, only elastic scattering. And we're interested in studying the particle production. And it turns out that if we just keep the Ising terms and the external field in the spin chain, it is too close to integrable, and we don't observe particle production. So we added an extra perturbation, a next to nearest neighbor perturbation that we can tune to get us far enough away from that integrable case so that the dynamics becomes more interesting. So what we have to do now is we're going to simulate this on a classical computer. And the whole idea is to find out how hard it is and to see what it takes to get into the regime where the classical methods fail. And that's where the quantum simulator will have a potential advantage. But what we have to do is pretty similar to what I already described. On our classical computer, we have to find the right tensors to give an accurate matrix product state approximation to the true vacuum and also to the false vacuum. We can find a description of the kink where we have false vacuum on one side and true vacuum on the other with an interpolating tensor, which we find by a classical algorithm. And we can likewise construct an initial state where we have a kink and an anti-kink with false vacuum in between and true vacuum on the outside. And then we can study its dynamics by a series of discrete time steps where after each step, we update our matrix product state description. And as the state evolves, it may become more highly entangled, in which case, to get a good approximation, we'll have to increase the bond dimension. The cost of the algorithm is dominated by the matrix algebra we have to do to find the matrix product state approximation, which is essentially a singular value decomposition. And that has a complexity that grows like the cube of the bond dimension. So here are some results from these classical simulations. What I'm showing here is the energy density relative to the vacuum, the energy per site, as a function of position on the spin chain, as a function of the number of time steps. In two cases, the first case, we're close enough to the integrable theory that particle production is suppressed. And in the second case, we are tuning to a non-integrable theory in which there is particle production. So in the picture on the left, you can see that in between the kink and the anti-kink, where there's a lump of energy, we have false vacuum, energy higher than in the true vacuum. That produces this confining interaction that brings the kink and anti-kink together so that they collide. And then because they can't escape because of the confining interaction, they're brought together multiple times, scattering each time elastically without detectable particle production. In the picture on the right, the non-integrable case, again, the false vacuum in the middle draws the kink and the anti-kink together. They accelerate toward one another, collide at relatively high energy, enough energy to produce new particles. And in this case, mesons are produced, which have the quantum numbers of kink-anti-kink pairs. Those particles are not confined, so they're able to propagate away from the collision region ballistically, which is the reason that we see energy filling the forward light cone of the scattering event. We can also study the entanglement produced in this process. So in here, for the two cases of the nearly integrable theory and the far from integrable theory, we look at the entanglement entropy in two ways. In the upper plots, we're computing the entanglement entropy as a function of the elapsed time across a cut right through the middle of the spin chain. In the lower plots, we're looking at how that entanglement is distributed, considering how the entanglement entropy behaves as we move the cut, sweep it across from one end of the spin chain to the other. So let's look at the upper plot first. This is the entanglement across the cut in the middle. So in the case of the nearly integrable theory, where we don't have particle production, we do find that as the particles repeatedly collide, the entanglement grows. It's able to grow even though there's only elastic scattering, even though there's no particle production. The elastic scattering of wave packets does produce an entangled outgoing state. That's because the phase shift in that elastic scattering process depends on the momentum. And when we have a wave packet, which is a superposition of different momenta, the wave packets become correlated in the collision. And as they repeatedly collide elastically time after time, that correlation becomes stronger and the entanglement continues to increase. And we find that as time elapses and the system becomes more entangled, we need a higher and higher bond dimension to get an accurate description of the state, so that by the end of this evolution, we had to increase the bond dimension to 128 to get a reasonably accurate approximation. And in the plot on the right, we're looking at the entanglement across the cut in the middle as a function of time for that far from integrable theory in which there is particle production. So we get a big jump in the entanglement in the first collision, in which mesons are produced, which propagate elastically, propagate ballistically. And you can see how the entropy becomes distributed as a result of that ballistic propagation in the lower plot, which shows how the entanglement varies as we move the cut across the spin chain. And here too, there are repeated collisions, and due to both elastic scattering and additional particle production, the entanglement continues to grow, so that at late times, the bond dimension had to grow to 128 to get a reasonable approximation. And that was as far as we went in our classical simulations. So one of the goals of this exercise was to get to the regime where the classical methods would break down. We didn't quite get there here. We were limited by the length of the spin chain that we simulated, and by not wanting lattice effects to be dominating, we wanted to keep the lattice spacing sufficiently small so that we had a pretty good approximation to the continuum. But at least we're creeping up on the regime where there's enough entanglement generated that the classical method becomes prohibitively hard. Okay, so I know I'm running out of time, so let me, in my last two slides, just make some concluding comments. So where are we on this program of simulating quantum field theories with quantum computers? We're just at the very beginning. What we've seen so far are estimates, which we did in our earlier work, of how the resources needed on a quantum computer scale with input parameters for scalar theories and fermionic theories. And there have also been extensive studies using classical tensor networks, like the one that I just showed you, of field theories in one dimension, including one-dimensional quantum electrodynamics, where there have been classical studies of both the low-lying spectrum of the theory and dynamical processes in which a string breaks due to the nucleation of electron-positron pairs. And there have been simulations at the few site level of one-dimensional QED in quantum platforms using both trapped ions and superconducting circuits. The largest scale such simulation that I know of was done by the Innsbruck group, which simulated the low energy spectrum of QED for 20 sites using 20 ions in a trap. There are various proposals, and I think you'll hear more about this from Ignacio Cirac when he speaks later in the year, for using analog simulators like ultra-cold atoms and optical lattices to study field theories, in particular gauge theories, in one dimension and beyond. So I emphasize again that if we're seeking quantum advantage, well, there are really two ways to go. One is to study higher dimensional theories, which are harder to simulate classically. If we want to stick with one-dimensional theories, which are easier to simulate on quantum platforms for the time being, then we should study processes that generate a lot of entanglement, where the classical tensor network methods fail. That could be because we consider a high-energy process with production of many particles, or a process in which many successive scattering events occur, which build up a highly entangled state. So what's the path forward for simulation of quantum field theories with quantum platforms? Well, we can anticipate that in the coming years, gradually the platforms will improve. We'll have more qubits, we'll have better precision, we'll have greater programmability of analog platforms. And it's important for the quantum field theory community to have access to a variety of platforms for this purpose, so that they can compare different algorithms and benchmark the platforms against one another in applications of interest. We should be trying to identify the stepping stones that we need to take to creep up on simulations, which will really be instructive from a physics point of view. We should continue to develop ideas for doing hybrid quantum classical simulations, where we can offload some of the computational tasks to classical supercomputers to save on quantum resources. We should continue to develop and improve protocols for the essential subroutines, the state preparation, evolution, readout, and the classical post-processing that we need to do. Quantum simulators are studies of the Hamiltonian formulation of a quantum theory, including in quantum field theory. The Hamiltonian formulation hasn't been as extensively studied as the Lagrangian formalism that's used in particular in Euclidean Monte Carlo simulations. So we want to continue to advance our understanding of the Hamiltonian formulation, understand better for the purpose of simulating gauge theories, how to maintain gauge invariance, how the errors scale, what type of renormalization group improvements we can do to get closer to the continuum and extract interesting physics. We may eventually want to have special purpose devices for simulating quantum field theory, as has been the case in the Euclidean Monte Carlo simulations, and a task for the near term is to clarify the hardware and software requirements for such a special purpose machine for QCD in particular. So I think in general, what we'll want to do in the near term with explorations of quantum simulation applied to quantum field theory is to illuminate the path forward, where we should be going. This is a long road, but it's a challenging and fascinating problem, and I hope some of you will be interested in joining the adventure. Thanks a lot for listening to me.
Well, thank you very much, John, for a beautiful talk. So we had more than 400 people attending live. Wow. And we can take some questions now. We're running a bit behind schedule, but I think we will find the time to answer a few questions. So Simone will kindly manage that, and you can please type your questions on the YouTube chat box.
So thank you for the very nice and inspiring talk, John. We already have one question by Vladimir Korepin, which asks well, does the entropy increase linear in time? I imagine that he refers to the plot that you were showing before during the scattering, this one.
Well, I don't know. Here's how it increases with time. It's an interesting question that in the case of the elastic scattering, will it approach an asymptote? It might well do so. It seems to be kind of rounding out. Also, it's interesting that we see these, some wiggles in the plot during the elastic collisions. So the entanglement dynamics is actually pretty complex, but I think there will be a limitation on how much entanglement we can get coming from the width in momentum space of the initial wave packets. The wave packets spread during the evolution, but we chose parameters so that they don't spread very much during the time that we simulated the process. In the case of the non-integrable theory, there's a big jump in that first collision when we first produced mesons. If we hadn't studied the case of the theory with explicit symmetry breaking, where there's a confining interaction, there would have been one collision which would have produced a burst of particles, and then from then on, of course, the entanglement would have stayed the same. There would be some fixed entanglement between the left movers and the right movers in that case. So in this case, because there is a confining interaction, there is a second collision, which is smeared out a little bit more in time, I guess, because of the way the wave packets were perturbed in the first collision. And we get another bump up in the second collision. And if we continued, I think it probably wouldn't continue to increase indefinitely for this initial state. So if we wanted to consider a process where we do generate more entanglement, we'd probably want to consider an initial collision with higher energy, and that might require us to study a larger system or to prepare the initial state in a different way.
Thank you very much. So there is yet another question by Stefan Schuster. But he's asking if, in your opinion, is cluster state quantum computation a good alternative or a possible alternative to what you have presented today?
I don't think I quite caught that. If what kind of simulation?
Cluster state quantum cluster state quantum computation.
Cluster state quantum computation, meaning measurement based?
I hope so. I think so. That's what would be my interpretation. Let's see if we have a kind
Well,
of.
I think that's probably platform dependent, whether one wants to use a measurement based protocol or some other method for doing the quantum computation. So, you know, in the case of our work on quantum algorithms, we've been focusing on, first of all, we imagine we have an ideal quantum computer, and we try to find a quantum circuit that does the simulation task with some bounded error. Then it's up to the hardware builder to decide how to implement our circuit using the hardware of choice. And measurement-based protocols are very natural. For example, if I want to do photonic quantum computing, for other platforms, it might not be the most efficient way of carrying out the simulation.
Thank you. Maybe we can take another question, even though we are so, and it's a kind of maybe a provocative one. So Ivan Kukulian asks comments that there seems to be a very powerful setup for simulating 1D quantum field theory already available, namely the atom chips. How do you comment on that?
Namely what?
The atom chips. I imagine it refers on BC.
Well, I don't know. I think if there is a particular hardware platform which is especially well suited for simulating one-dimensional physics, then we should, pursue that path. So the, I mentioned the simulations that have been done to date very briefly. In the case, actually, it's kind of interesting. I can say a little bit more about that. How the simulations of one-dimensional QED were done in an ion trap. And, of course, QED is a gauge theory, and that creates complications, which we didn't encounter in the simulation I described of a scalar field theory. But gauge theories in one spatial dimension are a lot different than in higher dimensions, because there are no propagating photons in one spatial dimension. The gauge symmetry really just imposes a Gauss law constraint. And so what one can do is solve that constraint explicitly. And then the theory, which in its formulation in terms of electrons and photons looks like a local, a geometrically local theory, becomes a no longer geometrically local spin system. And then one simulates that. And ion traps are very well suited for simulating the properties of a system in one dimension where interactions are not necessarily geometrically local. So if there are, but that was rather special to one dimensions. But that's an example of where the characteristics of the hardware platform were empowering.
Thank you. So the chair is telling me that we might have a final question, and maybe I would like to ask you. So the computation that you have just shown today seems to be perfect to be run on yet another platforms, which are Ridgway atoms experiment like Misha Luginez in Harvard or Antoine Braillet in Paris. So are you already thinking of doing something like that, or?
Yeah, I think Rydberg atoms are very promising. And there have been big improvements in just the last couple of years, which I think is an important lesson that Rydberg atoms have become a competitive platform in the last couple of years. Maybe 5 years ago, if I were giving a talk like this one, they wouldn't have come up for discussion. But we've already seen very interesting simulations of spin dynamics in experiments by the Harvard group. And I think it will be exciting to explore the potential applications of that platform to quantum field theory and other studies of chaotic dynamics, which we can do in the relatively near term in systems with hundreds of qubits.
That's great. And I think we can close question time with this insight. Yes, sir.
Well, thank you very much, Simone. Thanks, John. So maybe I can just share the screen.
Oh, here, let me get out of your way here.
Speaker. Thank you very much. And so let me. Thanks everybody for attending this first session of our quantum computation high energy physics seminar, the Quantep seminar. So most of the time we had more than 400 people attending live, including people from as far as India. So that's great. Thanks everybody. So I would just like to announce the next session, our second session by Professor Shaolan Wu on the 4th of November. She will be speaking about the application of quantum machine learning to high energy physics analysis at the LHC at CERN using quantum computer simulators and quantum computer hardware. And finally, I would like to thank once again our speaker, John Preskill, for his great talk, and also to thank all the team involved in setting this seminar and making it happen. So thank you very much, everybody. Thanks everybody for participating, and very special thanks to John Preskill for this wonderful inaugural talk. Thank you very much.
Thank you all for coming.